We're going to finish section 1.4 today, which was continuity and its consequences. And just as a reminder of where we were last time, we had talked about some concrete examples in real life about continuity. And then we had talked about the definition of continuity and this intuitive idea that somewhere along the way you probably had where somebody said something about if you can draw it without picking up the pencil, it's continuous. So everybody kind of remember where we were when we left off? All right. Now, this is our first example on this, and the directions are a little bit different than some of them that we've been working with on other things because of the changing content. It says to determine where f is continuous, and then, if possible, extend f to a new function that's continuous on a larger domain. So what this is talking about is a lot about that limit stuff that you did in section 1.3. So if we were asked to find the limit of this function, at a particular point, the point of interest would probably be the point x equals -1 that they would ask you about. Why?
Because that's what makes the denominator 0.
Yeah, it has that fact that the denominator is going to be 0 there. And so what did we do in section 1.3 when that happened? We factored. So that's where we're going to start on this content as well. So we're going to be looking at this function, and we're going to be asking ourselves, first, where is it continuous? The idea of it being continuous has to do with what we're allowed to plug into the values of the function. And so you guys have already established, looking at this, that x equals -1 is a problem, right? So I can't plug in x equals -1. But it's the only value that's a problem. Agreed?
True.
Okay. So when we're talking about it being continuous, the first thing we're going to say is that it's continuous. And I'll write it in several different ways so that you start to become familiar with our different options. We can say it's continuous in words. We can say at all values except x equal -1. So we can write it out in words. We could say it's continuous. So this is sort of one option here. Here's another option. I'll put it below it. We say it's continuous from -infinity to -1, and then -1 to infinity. So we're sort of writing it. This is called interval notation. I'm sure you've probably seen it before at some point. So it just tells you that it's continuous everywhere from the left until you get to -1. The open parentheses means you don't include the -1. Union means and including all these values that are about to occur after this symbol as well. So from -1 on to infinity. So it excludes the -1 because it's got parentheses. You may remember using brackets when you did use a value. For instance, if we were including -1, we'd use a bracket like that. You also might see something written like this. This notation just says x is a real number. This symbol is it doesn't look very good because I didn't draw it very well, but it's a symbol that says is an element of. Let me draw it a little bit better. Usually it looks like that. It looks a little bit like an E. It means is an element of, and this R with the double line is the real numbers. So it's a real number is what this is saying. And this is telling you what it can't be because we do have a location that it's not allowed to have that value for. X can't be -1. I don't really care how you write it, but I do want you to be familiar as we keep moving along because these different notations are going to come up from time to time. Okay? All right, so this is the first piece. It says determine where it's continuous. We did that. And then it says, if possible, extend to a new function continuous on a larger domain. That's where we're going to get into that factoring that we mentioned at the very beginning looking at this function. So, how in the world will that numerator factor? Yes. All right, and the difference of squares says I'm going to have what? Perfect. And then when I do that, I notice that, of course, the x plus 1s are reducing, which is why we wanted to factor in the first place, is because we had a feeling that might happen. And if I were then to actually take this function, that is y equal x minus 1, and I wanted to plug in, let me give it a different name. We'll call it g of x just for the moment. And if I wanted to plug in the x value of -1 that was causing the denominator to be 0, I would actually see that I would end up getting what value?
0.
Not quite.
-2.
This one's -2. Yeah, it's -1, not +1. So I would get at x equal -1, I'd get y equal -2. Now we talked about last time visually, what's happening in this graph with that location then?
There's a hole.
There's a hole. So there's a hole in the graph at x equal -1 and y equal -2, right? And otherwise, the graph actually looks like this one. It looks like a line, y equal x minus 1. That's what it looks like. It looks just like a line, but it's got a hole in the graph at x equal negative 1. So let me show you how we extend this graph next. Yes, Tammy, I'm sorry.
You used negative 1 because in the original one it would equal 0?
Because in the denominator in the original one would equal 0. It's the location where we excluded. It's the reason we used it in reality is because we marked out the factor of 0 in the denominator. Yep.
So negative 2 would be the limit.
Yes. Yes. When x is approaching negative 1, y would be approaching negative 2. So that would be the limiting value.
So in other words, this problem's good for the thing that messes it up.
Yeah. In many ways, you're right. And the thing that's going to mess it up is typically going to be a denominator equal to 0. All right, so let me show you how we extend this to a larger equation. And it doesn't matter what we call it, but we don't want to call it the name it started with. So I don't want to call it f of x. And since I've already called something else g of x over there when we were just working sort of like on scratch paper to the side, I'm not going to use that name either. I just don't want you to think it's that piece. So I'm going to give it the name h of x, but you can give it whatever name you'd like. And we're going to call this function h of x. It's going to have the same function it had before, x squared minus 1 over x plus 1. And it will have that value everywhere that x is not equal to 1. Because it can't have a value at negative 1, because that makes the denominator 0. And the other thing that we're going to let it be is we're going to let it be what we found by doing all of that reducing over there. It's negative 2. Oh, I'm sorry. Yes, thank you. You guys keep me on my toes. Absolutely. Thanks, Noah. And then the other value is that y equals negative 2, and this is when x does equal negative 1. So in a very real way, what we're saying is this is my equation, but it has a hole in it, right? And so I'm going to fill in the hole with this value. Does that make sense? I'm just establishing one more piece of this particular function that fills in the hole that I was missing. And that's what this is referring to. So it says, if possible, extend it to a new function. So we created a new function that has a larger domain. This domain includes the value x equal to negative 1.
So now we'll just have a vertical line go through that hole. I mean, a horizontal line.
Nope, you just have a particular dot.
Which is full.
Because it's only going to have this value of negative 2 at one point instead of at a series of points.
So if that, like, x equals negative 1 wasn't there, then it would be the line.
It would be a horizontal line. Yes. Yeah. Now let's try another one. It's got the same directions. The function's a little bit different. So the function here is now x plus 1 over x squared minus 1. Just sort of establish the fact this function right here looks a lot like the last one. What's the difference?
Reciprocal.
Yeah, so it's the reciprocal of the last one. It's a flip of the last one. I actually have my x squared on the bottom this time. So to start with, we can factor this and talk about where in the world, because this one's actually got a squared on the bottom. So this one has more than one location, at least potentially, where the denominator is 0. So I have x plus 1 on top. How does it factor on bottom again? Right, difference of squares. And I know I'm going to keep working with this later, but let's just answer the first question, where is it continuous? So what values cause problems, so to speak, on this particular function? Yeah, 2 of them, right? Negative 1 and positive 1. So we can write it out in words. I think you guys can handle that. This is continuous at all the values except negative 1 and positive 1. I'm going to show you what it looks like in interval notation because it looks a little different. This time we're excluding negative 1. But I am supposed to include everything between negative 1 and positive 1, and then everything after positive 1. So if we're writing where it's continuous, this is what the interval notation looks like. There's 3 different locations on the graph. There's the values before negative 1, between negative 1 and 1, and then after positive 1.
Why does 1 not work? I mean, a negative 1.
If I plug in negative 1 into this function, and I take negative 1 and I square it, I get positive 1. And then 1 minus 1 still gives me a denominator of 0. You can also think of it in terms of the factored form that we did over here. And you can see it maybe even quicker in the factored form, that this x plus 1 gives me a denominator that can't have an x equal negative 1, while this x minus 1 gives me the denominator that can't equal positive 1. So these two pieces tell me what the denominator, if I set them equal to 0, can't have in the
It's just
denominator.
like whenever I factored it,
Mm-hmm.
it came out as like 1 over x minus 1.
Right, but
So-
you're talking about reducing it. But the reducing location, which we'll get to in a minute, you're talking about taking and doing this to it, right?
Right.
This still gives me a hole in the graph. Having factored those pieces out, I'm going to get a hole in the graph at that location. So at x equal -1, I still have a hole in the graph.
Okay.
And so I still can't allow that function value in the original equation I was given. Do you have a question, Tammy?
Does it, when you plug in the positive 1 on the numerator, does it matter that it's not 0?
No. If I get anything of a 0 in the denominator, like the whole denominator to be equal to 0, it's a value in the domain that I cannot have, or it's a value that's not in the domain, is more accurate to say. So it'll change how I extend my function in a moment. That'll look a little bit different than the last one. But it still is a problem with the domain, no matter what happens on top. If I wanted to write it in, this is called set builder notation. I could talk about and saying that x cannot equal 1. You could even write it as positive or -1 if you wanted to consolidate like that. And then you can say x is real, or you could switch the order of that around. That'd be fine as well. So we've got real numbers, but not positive 1 or -1. Now let me go back to Tammy's question a little bit, because it actually leads into something else. So when we're able to do this canceling out, like I can with what I've marked out in purple, the x plus 1s, you guys know we get a hole in the graph, because we've talked about that last class period, right? There's a hole in the graph. I still have a limit value. Everything's good. So I've got a hole in the graph at x equal -1. But what happens at x equal +1? So over here, as many of you have already written down, because I've seen some of your papers, you've reduced this in this way, that this reduces like this. So since I can't cancel that denominator out, I don't have a hole in the graph at x equals 1. What's going on there instead? I have an asymptote. Okay, so and I have an asymptote, which means, and on this particular one, what it means is that on one side I'm going up at that location, on the other side I'm going down. So around the line x equals, which is a vertical line, x equals, +1, I've got an asymptote. So if one side's going up and the other side's going down, what can you tell me about the limit? Now that limit won't exist. So that's how it's going to be different, because I'm not able to cancel this out, because it didn't make the numerator 0 when it made the denominator 0. I don't have a hole there, so I won't have a limit there. Instead, what I'll have is I'll have an asymptote there. Now, this question didn't specifically ask us about limits, but that is how it's related back into section 1.3 and when we were talking about limits. Now, we haven't extended it yet, but yes.
So the whole purpose of this is just to cancel out the denominator?
It's not to cancel out the denominator. What it's going to do is it's removing locations where I have discontinuities. So if I'm able to cancel out the denominator with the numerator, or a portion of it, what I'm able to do is I'm able to remove one of those places that caused me problems with my continuity. So on this problem, I'm able to remove one of them, right? Because I was able to cancel out one of the pieces of the denominator. But the other value, I wasn't able to cancel out, so I can't remove that location of discontinuity. So when we create our function down here, oops, let me give it a different name. I'll call it k of x this time. Just like the last time, one of the values is going to be the original function, and the other value is going to be, well, actually, let me pause on that. Let me finish that piece. All right, so one of them is the original function, and it's the original function only for the values where it's not equal to 1 and -1. Agreed? Because I don't have values there. I can't plug those values in. I'm really struggling on those denominators, aren't I? Thank you. Now, we didn't finish this back up here, but in this particular function now, what if I let x equal to -1, the location that I actually was able to remove? What would I get? Yeah, 1 over -2 or -1/2, right? So that's my value down here. This is what I did on the last one too. This is my value x of what y equals -1/2. It's the location where I'm filling in the hole, and I'm filling it in at what x value? -1. Now you notice I don't have the ability to do this at x equal -1, because neither the function I started with nor the reduced function I've ended with allow me to plug in 1 in the denominator. Agreed? So I don't have the possibility of extending this to all of the x values, the entire set of x values. But I'm able to extend it at least to 1 additional x value to make the domain just slightly bigger to fill in 1 particular place of discontinuity. Now, I can't remember if I put it in this one or not. I don't see it. I've used the language, so it's probably good for me to actually tell you that when I talk about discontinuities, there are 2 types of discontinuities, and you see them both happening in this particular equation. One continuity is called removable, right? We were able to actually fill in the hole and remove the discontinuity. So on this particular one, that x value of -1 created a removable discontinuity because of the factoring. I mean, that's why. The factoring allowed us to remove the discontinuity. The other value at x equal 1 is a non-removable discontinuity. I am not able to simply fill it in. And the reason I'm not is because it's not a hole. It's an asymptote. And I can't fix an asymptote by filling in a hole. Okay? All right. There are 3 things that have to be true for your function, or that are true, I should say, when your function is continuous. So for an f to be continuous, this was the previous slide, and I'll go back to it in a minute. What the definition of continuity actually said is that, first of all, your function has to be defined. That means it must exist at that location. It has to have a y value. Secondly, the limit has to exist. And thirdly, the function value and the limit have to be the same. So if you're taking a look back over here, this was the definition it's referring to for continuity. This piece right here is what that remark is referring to. It's telling you the limit has to exist. That's the left-hand side. It's telling you the function value has to exist. That's the right-hand side. And the third thing is it's telling you they have to be the same thing. So when you're actually testing for continuity on the next problem, we're going to test those 3 pieces of information. So it says explain why each function fails to be continuous at the given x value by indicating which of those 3 conditions, those are the conditions up here in this remark, fail to exist, or which are not met. Okay? So the first condition is the condition that the function value has to exist. So my function is f. The function value that we're being concerned about right now is at x equal 1. What happens at f of 1? What's going on? Denominator is 0. So if the denominator is 0, the function value does not exist. Okay? So f of 1 does not exist. Abbreviate it D and E. So this one fails. All right, condition 2 says that the limit value has to exist. So the limit as x approaches 1 of the function is supposed to exist. Well, think back in terms of the graph of this equation. What will the graph of this equation, what will it be doing, let's say, when x is getting close to 1? From one side it will. So graphically, before you ever showed up in calculus, if you looked at this equation, this has an equation that's going to have what happening at x equal 1? An asymptote, right. So if it has an asymptote, that means on one side it's, well, this potentially, and on this one it will. On one side it's going up to infinity, like you said. On the other side it's going down to negative infinity. So what can you tell me about that limit? It's not going to exist because one side goes to infinity, the other side goes to negative infinity. So this limit doesn't exist. This is so condition 2 fails. You don't always fail all the conditions, but on this one we will. The third condition talks about these two limits, this limit rather, and this function value being the same. Well, obviously they can't even make sense to be the same because neither one even exists. Make sense? We can't even talk about it in that way. It doesn't even make any sense to talk about. So this one is sort of irrelevant. Because the function value and limit don't exist. So this one actually fails everything. It fails every possible problem that there is, or every possible portion that we checked of that definition, right? So that's what's going on that one. All right, so let's talk about continuity of some other types of functions. And we've talked about limits with these functions before, so this is sort of a continuation of that idea. Polynomials are continuous everywhere. And that should make sense because we talked about in the last couple of sections, one of them about the fact that they have limits everywhere. So if they have limits everywhere, they're continuous everywhere. That's going to work, and they're defined everywhere as well. Additionally, sine and cosine, same thing. They're continuous everywhere because their functions are defined everywhere. They have limits everywhere. Another one is we have the nth root of x. It's continuous for all x values. And this is sort of sounds funny. We did look at this briefly before too. But of course, when the nth root is an even root, like a square root, we can only have positive values underneath the square root. So it talks about when n is odd, it's for all the values. And then for when the n is even, we only have values x greater than 0. We can only talk about the limit greater than 0, continuity greater than 0. Okay. If it's an odd root, like a cube root, then you can do it everywhere because you can take a cube root of a negative number, and that's okay. Okay, a few others down here. Theorem 4.2 says, if f and g are continuous, then you automatically get that f plus and minus g are continuous, f times g is continuous, and f divided by g is continuous. And of course, on the third one, we've got that extra condition that you can't have 0 in the denominator. So g of a can't be equal to 0. And these are all talking about continuity at one particular point. So at one particular location for x equal a, and then the a can be whatever we've used in that particular function that we talked about continuity for. So if we were talking about a polynomial, a could be any real number. But if we were talking about a square root, a would have to be positive. Okay?
So we did, on our homework, we found two functions that weren't continuous, but were when you multiplied them, so this is kind of the opposite.
Yeah, and you didn't do it for continuity, you did it for limits, but there is a relationship between them as we've discussed. Yes. So you were looking for something that had these kinds of features where when you added them together or multiplied them together, it removed the problem, but when they were separated out initially, there was a problem. Yeah, and so this is the reverse. This is telling you that if we know that there's no problems, right, for f and g, they are continuous, then when we add them together or multiply them or divide them, we still have no problems. But again, it doesn't tell you the reverse, right? It doesn't tell you if you have this wonderful, beautiful thing that's continuous everywhere, that when you sort of separate it out in some way, that you're also going to have two things that were already continuous to begin with. You may or may not be able to do that. It depends on the functions as you separate them, which is what you were doing in your homework. Okay, and we did an example of last class as well. All right, another theorem. Theorem 4.3 says that suppose you have a limit for a function, and its limit, the value is L. And then you are doing a composition of functions, one function inside of another one. If that limit is at L, if it exists, right, they're saying that limit exists and it's continuous, then if you compose that function inside, you're able to actually do that limit inside. We'll see an example so you can see how this is working. But this is going back to the idea of continuity. If you were working with something, for instance, say you had a square root, and we talked about the fact that we have the square root of x plus 3. Well, if I want the limit at x equal 1, it's going to exist because I can plug in the number 1 there, right? There's nothing wrong with that. So if I want to talk about that particular function, it's going to have a limit value at x equal 1, right? Well, what if I take that and then I put it into a denominator? So I put it into another function, the function 1 over something. Well, the limit's still going to exist at 1. There's no problem with that because it originally existed at 1. Are you with me on that? That's all that's saying, is that if you have that limit value, then you're able to actually compute it. Then you can put it into something else and do the same thing again. Okay? Like I said, we're going to see another one of those that's not this example in a moment.
So if your x value was -3,
Uh-huh.
then it wouldn't work in your...
Right. This theorem actually only talks about when it does work.
Oh.
But you're right. If this x value were -3, we would have a problem. And actually, if you take a look back over here, this is actually only talking about when x is strictly greater than 0. That is strictly greater than 0 underneath the square root. And the reason is because if it is actually equal to 0 underneath the square root, the function exists, and that's fine. It has a value, but there's nothing happening over here, so you can't approach from both sides. Right? And that's a problem, because limits have to be able to be approached from both sides. So we exclude the value 0 on purpose anyway, so it wouldn't actually end up mattering on this one to create a problem with denominator. Yeah. All right, corollary says, suppose that g is continuous at a, and then f is continuous at g of a. Then the composition f composed g is continuous at a. And just to remind you of this notation, f composed g, we'll say it this way, is f of g of a. And the way you did this back when you learned about this in an algebra course is you said, okay, I'm trying to find f composed g, so I'll find what g of a is first, and I'll get a value for it, and then I'll plug that into what the f function is. Okay? Or if you didn't have a specific numerical value, you might have plugged this equation in for the x value in the function. Okay? This isn't going to come into play significantly, but we are going to see an example so you can see how this is actually interacting with what we have. All right, last one for now. All right, one more definition virtually before we do a couple of examples. Interval continuity. So if f is continuous at every point on an interval, a to b, we would say f is continuous on the interval ab. We noticed that notation, we saw it before. Similarly, if f is also continuous at the end points, at a and at b, we would say it's continuous on the interval, closed interval ab. So you have those brackets. Remember I mentioned those just a little while ago, those brackets. Finally, if it's continuous on the interval negative infinity to infinity, that is at any value, like we did for polynomials or trig functions, sine and cosine anyway, then we say that it's continuous, period. We don't actually specify. So if you hear something said that it's continuous and it doesn't tell you where, they're telling you everywhere. Okay? So when we say a function is continuous and we don't specify at a specific location or an interval location, we mean everywhere. All right, so we're going to do an example. This one is a function inside of a function, right? You've got a cosine function, but inside of that cosine function is not just cosine of x, right? It's not just cosine of x. It's cosine of 1 over x. So it's determine the intervals on which f is continuous. So there is a problem here, right? I can't plug in just anything I want. But if it were cosine of x, I could. Yes? That's what this theorem we had earlier said, is that the cosine graphs, oops, I passed it right here, that polynomials are continuous everywhere, that sine and cosine are continuous everywhere. So why is this one not continuous everywhere? Yeah, because inside of it is another function. It's a composite function like we wrote down over here. It's f composed g. And what's inside of it is what we basically have is we have our f of x function is the cosine of x. And my g of x function, the one that's inside of it, is 1 over x. So back in an algebra course, you were told that if you did f composed g, this would be cosine of 1 over x. So the fact that something inside of it is another function, and that function inside's got an issue, means now cosine's got an issue too. So it is, in fact, exactly what you said. It's got the issue at x equals 0, right? So we're going to write down a little bit of what we've just said so that when you look back at this, you'll remember what the deal was. Cosine is continuous everywhere. But 1 over x is not continuous at x equals 0. Therefore, f of x, which is the cosine of 1 over x, is continuous, not everywhere, right? But on the interval negative infinity to 0, and then 0 to infinity. These directions specifically tell us that the answer is supposed to be in an interval form. And we had examples earlier where I said you can just describe it, you can write it in these different ways. That's not the case. These directions are pretty specific. They say an interval form. So this would be the interval form. It includes all of the numbers from negative infinity until I get to 0. The open circle, or the open parenthesis here in this case, is indicating that I cannot include the number 0. But then I can also go from 0 to infinity afterwards. Is everybody good with that? Okay, let's take a look at one with context. We actually have a function given here. It's called a piecewise function. I created one of these before. I didn't tell you it's piecewise. But it is a piecewise function. And this function is a state's income tax table that's code. So it says, suppose the state's income tax code states that the liability on X dollars of taxable income is given by this equation. The directions say determine the constant C that makes the function continuous for all X. And then it says to give a rationale why this kind of a function should be continuous. So we'll do the rationale last, but let's just work on the part where it is we figure out what C is. So in order for a function to be continuous, it had to satisfy 3 conditions. This is back at the very top of the last page that you have of your notes. Remark 4.1. The function value has to be defined, the limit has to exist, and then the function and the limit have to be the same. Right? So in essence, what that means is that if I come at this function to the value, whatever value I'm looking at, from the left and from the right, they have to actually meet at the same place. Agreed? And it has to be a filled-in circle. I can't just sort of meet there with an open circle either, like we've seen some of the cases happen to be. So this function has 3 parts to it. And if you'll notice, the first part and the second part, these 2 parts don't have C in them. Agreed? Now, if you take a look here at x equals 0, we're supposed to be on this first piece of the function, and I've got an x value of 0. Now, if I'm slightly bigger than 0, I'm supposed to be on the second equation, the second line of the equation, right? And if we actually did plug in 0 here, what would happen to 0.14 times 0? I'd get 0. So these 2 pieces are already continuous, right? So if I were to graph these, the first line tells me that if I'm to the left of 0, I'm supposed to be at 0, like this. And then once I hit $0, slightly more than making $0, I'm going to be going up on a line. So this point has a sharp turn right here, right? I'm actually making a change in my slope, but it doesn't have any break in the graph. So the first 2 lines are perfectly fine for continuity. The second line and the third line are the problem spots, because the second line and the third line, well, the third line specifically has this value of C in it. So what we want is we want these 2 values to actually approach the same thing if I came at the value from the left and the value from the right. Now, if you look on the notations here, if I'm slightly less than $10,000, because that's what this X is representing this problem, $10,000. If I'm slightly less than $10,000, I'm on the middle line of the equation. And if I'm slightly more than $10,000, I'm on the larger line of the equation. I'm on the third line of the equation. So far, so good? So what we want is we want the case to be that if we were going to come at this value of 10,000 from the left, which would be something slightly smaller, and from the right, which is something slightly larger, that we hit the same value. We want their values to be the same. So what we're going to do is we're going to write that down. We want 0.14x to equal c plus 0.21x. We want them to be the same. But we want them to be the same at a very specific point in time. When? At 10,000. Right. So we want this to happen at x equal to 10,000. So I actually want this to do this, but I want it to be done when x is equal to 10,000, so we're going to plug the 10,000 in. So this is just a little bit of multiplication, subtraction, right? So what happens when I do the 0.14 times 10,000? What do you guys get? 100? 1,400? And then that means I would get 2,100 over here, right? So somebody tell me, what's C? Negative, not 7,000, 700? Okay. Negative 700, it's okay. So C would be negative 700. So this one says, find the constant C that makes the function continuous. So we did that part. We found the value for C. C has to be negative 700 for that to work. Negative 700 isn't a dollar amount. All it's doing is it's actually compensating for the fact that when I plug in a value here that's, say, like $30,000 or whatever, I'm going to get times 0.21 was like 21% tax, basically, and then subtract off the 700 from the C. That's what's doing. Let's talk about the rationale, though. Do I have space for that on this? No. So I'll talk, you guys write them. Why would this have to be continuous? This is about taxes, right? Why would it make sense for this to be continuous?
Because if there was a hole in the graph, it wasn't continuous, you would be able to calculate the tax.
Well, say again? Well, if there were a hole in the graph, there would be no tax. You're absolutely right on that. And I'm pretty sure that the government wants our taxes. Okay? So yeah. What if there were a jump? Because another way to have something as a problem would be there was a jump. Like if this number weren't negative 700 here, oops. If I didn't have negative 700 and I had something like 600 or negative 2,000 or something like that, instead of a hole in the graph, I'd have a jump in the graph. What would be weird about that?
They wouldn't get taxed on the money in between the two values.
No, because that would be a problem with your x values.
Your taxes would jump huge.
Yeah, there'd be some weird jump in your taxes that would be strange. Either a jump down or a jump up. And that would be sort of like discouraging you from making over a certain amount. Now, unfortunately, our tax code with our federal government does have some problems with it just like that. But this would make sense, right? The problem wasn't about what really happens. It was about what would make sense. Didn't it say that? Why would this make sense? The rationale has to do with this sort of this incongruous idea of, okay, what if I made $10,001 then? Well, it should be pretty close to what happens when I make $10,000 or $9,999. The taxes shouldn't be drastically different. They should be very similar. So that's the idea of the continuity in the problem. Does that make sense? Okay. All right, and we're going to talk about that idea again happening here on this intermediate value theorem. Intermediate value theorem is a pretty important thing. We're going to talk about another theorem that has some similar ideas to it when we get further into our textbook. This one's called the Intermediate Value Theorem. It says, suppose the function's continuous. Okay, so in your mind, you have an image of what that looks like. Whether it's back from when somebody talked about drawing the curve without picking up your pencil. It doesn't have these jumps, no asymptote, no holes, all those kinds of things. So we've got something that's continuous. And W is a number between f of A and f of B. So let me draw you a picture of what's happening. So you have A and B. I know I'm writing on top of the other definition, but just pretend for a moment. There's A and there's B. And they have some kind of a continuity like this, right? It's smooth, or not necessarily smooth, but it's at least not got any problem spots with jumps or holes, okay? So somewhere in here, that's f of a. And somewhere in here, say about right there, is f of b. And it wouldn't have to be that f of b is bigger. That's how I drew it. This is telling us that w is a number between f of a and f of b. So something in here somewhere. It doesn't have to be halfway between either. It's just somewhere between them. This is saying that if that's the case, if the w is between the f of a and f of b, then it would have been impossible to not have this happen. There must have been a location between a and b that corresponded to that y value. Right? It can't have gotten left out. And it can't be not between them either, because if it were not between them, then we would have something that had a hole in the graph or a jump in the graph.
And since we're told it's continuous, we can't.
Exactly, but since we're told continuous, it can't happen like that. So all this is saying is exactly what you know to be true, right? So this is the idea that if you're driving and you start out 0 miles per hour because you just started the car, and at some point in the drive you hit 70 miles an hour, then what that means is that at some point in the middle of that drive, you were also at 60 miles per hour, right? You can't jump over the 60. Okay? Same thing we talked about last time with your cholesterol was our example, right? If the cholesterol went from, I don't know what cholesterol numbers are, but if it went between two numbers, it had to have passed through every number in between. Right? That's what the Intermediate Value Theorem is saying. So at some time, it was at that value in between, because time was our independent variable there. Now, a corollary to this is actually quite helpful, says that if you have that function that's continuous on AB, and then f of a and f of b have opposite signs, in other words, one of them's above the x-axis and the other one's below the x-axis. So just take my picture in your mind and sort of move it down, so that one's on top of the x-axis, the other's on bottom of the x-axis. Then somewhere in between that highest point, that lowest point that we're referring to, it had to cross the x-axis. That's all it's saying. It had to have crossed the x-axis for that to happen. You can't jump from being above the curve to below the curve, or vice versa, and not actually cross through that axis. And that's what we're going to do the example for on the last example. All right, so it says use the intermediate value theorem to verify that f of x has a 0, okay, that phrase has a 0 means crosses the x-axis, on the given interval. So this is a very easy process to verify. What we have to verify, according to the corollary, is that one of the values on the endpoint was a positive value and the other value is a negative value. So we're going to evaluate our function at 2 and at 3. So if I plug in x equal to 2, what function value do I get?
-3.
Yes, this is 2 squared minus 7. This is -3. And what about at f equal 3? I get 2. So this one's negative, and this one's positive. Agreed? All right. So we're going to write something down like this. Since f of 2 is negative, or if you want, we'll use some notation because I already wrote the phrase out like that. F of 2 is less than 0, and f of 3 is greater than 0, then there exists C between A and B. The A and the B here are 2 and 3. Where f of c equals 0. Somewhere between 2 and 3, the graph crossed the x-axis. It had to, because it went from being negative to being positive. And it can't go from negative to positive if it didn't cross through 0. And that's all you're saying. The words are just as important as the notation we did. Okay, this language that I wrote down here, you don't have to have complete sentences, but you should have a complete thought about what's going on here. All right? You should cite I didn't say this, but I should too. You should cite by the Intermediate Value Theorem. I'll abbreviate IVT, Intermediate Value Theorem. Okay, the Intermediate Value Theorem, or you could say the corollary to it. Yeah.
Corollary for which is part of the intermediate value?
It's just a specific example of the Intermediate Value Theorem. So it's just, if you see, take a look, the only difference between these, whoops. The only difference between these two statements here is that the corollary here makes it for sure that one of the values was negative, the other value was positive. But the Intermediate Value Theorem makes it more general. It's saying any two values would have this feature. And then the corollary is saying, specifically notice, if one's positive and one's negative, you're going to have to cross through 0 itself. So there, the second one, the corollary, is just a more specific case of the theorem. Yeah. Okay, any other questions on these ideas? All right.